All right, everybody, we'll go ahead and get started. We'll catch up where we left off on Wednesday with functions. So we're going to write some more functions today. Where we're headed in the class, next week is all normal, but the week after that, we have Monday off. So just as a heads up that there is a Monday vacation coming. So we won't have any lectures or anything on that Monday. The remaining 3 weeks of class, which is what we're coming up on now, like I said earlier, we're going to switch gears to more of like the practical side of MATLAB, of using it like a really nice calculator to solve some of the more annoyingly long problems that we typically have in a lot of engineering classes. That's going to make a lot of use of functions as we go, because often we're trying to solve functions for some value, so we need to be able to write the functions in the first place. So there is a reason why we're doing what we're doing today. Let's switch over to Canvas really quick. I just wanted to show you where I'm going to get a bunch of files today. Let me make sure that that actually shows up, which it does not. There we go, now it's there. We're going to use those block simulations from homework 3. So if you go into modules over here into homework 3, the solutions for homework 3 have been posted up here at the top. And we're going to mess around, I would say, primarily with A and B. I don't think we'll have time to get to C today. But I want to use those as sort of a platform to illustrate why you might want to use a function. So we're not going to add any functionality. No? Nobody? No? Okay. We're not going to add any functionality to that, but we will add functions to that particular problem. It's okay. I enjoyed it. You didn't have to enjoy it. So if you want to grab A, B, and potentially C for the solutions, we're going to be copy-pasting some of that code around. While you're doing that, I'm going to switch over to Excel and just review a little bit about functions from last time, because we're going to write a bunch this time. So this was the sort of workspace idea that we had finished with on Wednesday, about how the only way to pass information back and forth between essentially a script, which operates in the base workspace, and functions, which are convenient organizational tools, is through inputs and outputs. And today, the first thing we'll practice is figuring out what an appropriate set of inputs and outputs are. But then after that, we're going to come back to this set of notes and modify it for local functions, which are written effectively the same way as standalone functions are written, just a little bit more conveniently because they get organized into a script. It mildly changes the way that they can be used, but for the most part, they are used the same way, whether they're local functions or standalone functions. But the idea is, remember, we don't pass the variable itself back and forth, we only pass the value. And because of that, the naming can get a little bit funky, because in the function, a variable can be thought of as one thing, and in the script, it can be thought of as another thing, and they might be conceptually linked. And that's what we're going to do today, or at least practice doing today. So let's go over to MATLAB. We'll practice a few functions and then come back here and talk about local functions. I've given myself a new folder here over in the current folder. I'm going to go grab those homework solutions. Since I wrote the solutions, I happen to have them all. So I'm going to grab those really quick. Let's just grab A and B right now. Remember that functions have to exist in your current folder. There are some games that you can play to make a function be found if it's somewhere other than your current folder. It just becomes a headache. So I recommend you keep the functions in the folder you're working on. If you need to call them, put the script that's calling them in that same folder so that you don't have to mess with your working directory or your current path or anything like that. So the first thing we're going to do is create a script which mimics the behavior of the blocks. So this is the solutions that I posted for part 3 of the blocks, problem 3 part A for the blocks. Just as a reminder, what we did was we initialized our simulation for part A, it was one block, and it was going to bounce back and forth between 0 and 10. So we gave it an initial location, an initial velocity, and then did a little bit of pre-allocating and stuff like that. And then there were a number of different ways that we could do the simulation. I chose to use a for loop, which seems like a good choice here. We incremented the position of the block, and then I used an if and else if statement to check for wall collisions, which should at least look conceptually similar to the stuff that we did for the ideal gas and what you're doing on the project, even if the code looks slightly different from the way that you're doing it. So I'm going to duplicate this over in a new script, and I'm just going to call this script A. This script will use standalone functions. You don't have to declare that. I'm just making a comment up at the top of the script so that when you go read this, you'll understand why did we come up with two separate scripts. And that's in contrast to the local functions that we'll use at the end of class. So I'm going to copy paste all of this from part A over into our script over here, except for that little comment up at the top. And what we're going to do is replace all of the contents in here. So we're going to keep the for loop that sits inside of here. We're also going to delete the analysis for now, just because we don't need the analysis. And we're going to focus on writing functions to do exactly the same thing that we've already done, but to illustrate how the syntax of the functions can be at the same time both helpful and also confusing. So we're going to look at it in a couple of different ways. The first thing we're going to do inside the simulation is get that x old value, which is going to come from x of I minus 1. And then something's going to happen in the middle. And then when we're all done, we're going to have an x new value, and we're going to want to store that x new value at the current location in I. So we'll say x of I is equal to I new. That sort of a syntax is probably more familiar than some of our other ones because it's the same thing we've been doing for the ideal gases and for the random walks and for your project. We're taking its previous location, we're going to update it somehow, and then store that new one. The things that we're going to do in the middle, we're going to write three functions. The first function that we're going to write is update position. To do exactly that, it's going to update the position of the particle. So this is going to be like Newton's law. We're going to write another one, which we're going to call check right, and that's going to be a detection of right wall collisions. And then we're going to write a third one called check left. You could probably guess that's checking the left wall collisions. Whether or not you would choose to create functions of this particular set is kind of up to you. Remember, the computer doesn't care whether you use a function or not. Functions are there to make your life easier, to sort of take away some of the complexity of the code and say, within this function, I'm only going to worry about one thing. So I don't have to hold the entire code in my mind all at once. I can say, all I'm dealing with is this specific aspect of the code. This one, as you'll see in a moment, okay, maybe we didn't need as many functions as I've done here, but it's designed to get you thinking about how to use functions. So that update position one, the first thing that we ask ourselves is, what's the minimum amount of information we need to update the position? Well, we would need its current position, i.e. x old, we'd need its velocity, and we would need the time step that we're going to increment by. So right away, that tells us something about update position. What we're going to end up with is something like update position, and then we need to supply that information. It's going to end up looking something like x old, u, and dt. Right, those have to be the inputs that we're going to do, because that's the minimum information we would need to update a particle's location. What do we call the result? I mean, historically, we've been calling it x new, so I'm just going to leave it as x new. Notice what we don't return as an output of this function. We don't bother returning u, and we don't bother returning dt. We needed it as an input so we could calculate x new, but no matter what those are, they don't have an effect on changing u or dt, so there's no point in returning them because they're just going to be the same thing as we go. So that's one of our functions. Let's go write that one right now. And I'll put the functions next to each other so that you can see them. So as soon as I know that this is what I want the syntax of my function to be, I know that that's got to be more or less the first line of my function file. So I would say something like function, and I could say exactly what I wrote there, which is x new is equal to update position of x old, u, and dt. You know, I really don't like their habit of this gray bar here where the numbers are. It used to be about a quarter that wide. It was just wide enough to handle the numbers, and for some reason it's really wide right now. Oh. Anytime we write a function, there's two things you can do really quick. One is add the end at the end of it, and two is save it and make sure that it's got the same file name as the function itself. Which when you go to save something, you should just be able to click save here because MATLAB will auto name the file to match whatever the function name is. So here's where I'm going to sort of abstract away a little bit. Yeah, it is x new over here, but for example, one way that we called this in the project was x0 and then no subscript on the other one. It's not necessary for those inputs and outputs to match the way that they're being called in the script. You can call them whatever you want. We could call that A is equal to something and then B and C and D if we wanted to, as long as we know what they mean. So the way that we would write this would be x is equal to x0 plus u times dt. When we call it, we're passing the variable or the value of the variable x old to the function and treating it as though that's x0, right? Within this update function, well, within the update function, update position function, there, I finally said it correctly. Within that environment, x0 will have a numerical value equal to x old. It just so happens that we chose u and dt here to be the same over here, but that was not necessary, right? We could call those anything we want and the script would work. Both things would work okay, as long as we were consistent. So I'm going to save that. So this is an example of what I said earlier of, do I need to write a function to do that? Probably not, right? It's only one line on there, but we're using it as an example of how to write a function, which is why we're doing it here. The next function that we have to write is one that I'm going to show you the syntax, but then shut up for about 5 or 10 minutes and let you try to write the remaining two functions. The syntax for the other two have to be check left and check right, so we need to check for wall positions. So for example, we're going to end up with something like check right, and we have to ask ourselves, what would the inputs be? What's the minimum amount of information I need in order to check whether the collision occurred at the right wall? The minimum amount of information I would need is that new value of x that I just calculated in the line above on line 15. That's all I need to check the collision. But if I want to implement a reflection off of that wall, implement the actual collision, I also need to be able to supply u. Because if I don't supply u, then I can't flip its sign inside of that function. But I don't need dt because I'm not changing anything about the time. Given that there's the possibility that I could adjust both x new and u, I need to be able to return both of those as variables. So I could say something like x new and u is equal to check right of x new and u. So the way to read this, remember MATLAB reads it from right to left. So it'll evaluate this function. It'll pass the values of x new and u in to that function. It'll do something to them. And then that function check right has to be able to return a value of x new and u no matter what happens. So it needs to be able to evaluate the cases for both a collision and no collision as well. So I'm going to do a couple of things here. First, I'm going to move that old code over here so that you can see it in case you need it as a reminder. I'll leave the update position visible just if you want to use that as a reference. Give us some space here. And so what we're going to do is take about 5 to 10 minutes and try to write as much as you can of the check right and check left functions. And there's more than one way that you can write those functions. We'll write the check right one way and write the check left another way when we come back afterwards. So I will leave this here and we'll just work for a little while. If you're watching over on Twitch or working along, I am over in Canvas chat, so feel free to throw questions over there as well. But we'll come back around like maybe 3:20, 3:25, something like that. All right, let's take a look at a couple of different ways to do this. So I'm going to leave the old simulation visible over here on the top right, because that's got all the logic that we need, and then we'll just create our new functions down here on the bottom. Even though we're not actually running this function, it's nice if the logic is there, so in case we need to refer to it. I need this check right, so the first thing that I'm going to do is create that as a function. So I'll say function, and then what are my outputs going to be? They're going to be x, new, and u, if I wanted to keep them in exactly the syntax that I used for the previous one, or that I already wrote in the script. So this is going to be check right, and then I need to supply the inputs, which are also x, new, and u. But even here, we can do the same sort of thing that we did in the previous one, the update position function. We don't have to call them the same thing if we don't want to. It's up to us. So for example, we could call this x0 and y0 and call the outputs x and u. And that's one way that you can use a function to help yourself sort of keep track of what's being changed and where. The inputs to this function are always the old values of x and u, right? No matter what goes into it, those are thought of as the old values. And the values that are returned are the new values, which we're just calling x and u. Because of the way that we've defined this, no matter what happens to the function, it has to return a value of x and u, no matter what the decision is on the inside. Because of that, we're going to use an if-else statement. So the if part is going to ask if x0 is greater than 10, that's our right wall collision. If it is greater than 10, then the value that we're going to return is equal to 20 minus the value that came in. So that's our update position. And similarly, the value of the velocity that we send out is going to be equal to minus the velocity coming in. And so that can be nice. I need a little zero here, u0. That can be nice because each one of those lines of code sort of clearly distinguishes between I'm using an old value and using a new value. The else condition here is that there was no collision. So here, the old values are the same as the new, and so we'll say x is equal to x0 and u is equal to u0. And we have to do that little bit of extra coding there because of the way that we define the function. We said we're going to provide outputs as x and u based on inputs which are x0 and u0. So anytime we have those inputs, we have to be able to always define both an x and a u. Notice we wouldn't want to use an else if statement here because we need it to happen, right? Either there was a right wall collision or there was not. There's no other option that we can use. We could play a slightly different game depending on how we choose to write the function, which I'll do with the check left function. So we could say something like function x and u is equal to check left of x and u, which may or may not look confusing or straightforward depending on whether or not you like that kind of syntax. The one way to interpret what's written there is take whatever the values of x and u are and just update them, right? Overwrite their old values with a new set of values. Because of this, we only need to check whether or not there was a collision occurred. We don't have to worry about the case where there was no collision. So we can say something like, if x is less than 0, really update the position. So we would say x is equal to minus x, that's updating the position. And u is equal to minus u, that's updating the velocity. And then end. We don't need the else case here because if this element is not true, if the condition for this if statement is not true, that's okay. The inputs will simply become the outputs, right? They won't get changed at all. They'll just get passed through without any kind of a change. Either one of these are entirely equivalent, right? Whether I do a check left like this and just pass stuff through, or I want to do a check right and explicitly define what happens in no collision, it has exactly the same behavior. So it only becomes a question of what makes more sense to me when I'm coding it. Do I like to always keep track of old versus new, or am I okay doing sort of some of the what might be considered a coding trick of knowing that that operates from right to left, and we'll simply update the values as it goes through. I don't know. There's no inherent advantage to either check left or check right here. They'll take the same amount of time to execute under basically all conditions. There's really no difference between those two. Both of them would have very similar syntax over here in the script as well. They would still be x new is check either left or right of x new and u. The reason for that is because they need the same values of the variables that we have. So we took x old here and updated it to x new, and then the check left and the check right are ways of further correcting x new if we needed to. That's where it would get confusing if you always wanted to call them old and new. You'd have to start coming up with like subscripts, right? New after the update position, and then old, and then new after the check right, and then old. Like it would get really confusing if you needed specifically an old and a new before and after each of those functions. So I'll throw one more line down here just to plot x. We'll just omit the time for now, but we will label it just so we know what's going on. On the x-axis is iteration, and on the y-axis is the x position. So if I haven't made any mistakes here, I should be able to run this. I don't know what just happened there. That was supposed to go over with the other one. Get yourself in there. Okay. It doesn't want to behave. It's just switching back and forth. Anyway, let's run that, see what we get. So there's our plot, which appears to be what we wanted, right? This was for one block sliding back and forth. We did skip the time element here because I didn't want to, time's not critical to what I was trying to get at here, which is the use of functions. And now you have to ask yourself whether this is easier to read, easier to interpret than having it all put together as one big script. Because that's the only reason that you would need to write a function here, is if it helps you. The computer does not care one way or the other. It'll run at the same speed and have the same effect. So the majority of the time when you're writing functions, you write them to help yourself, not to help the computer go faster. But here it would be a little bit easier to, for example, track down a bug if something was going wrong inside of that plot. If the left wall was working but the right wall wasn't, I know exactly where to go to check the right wall stuff. It's inside of a function called check right. And that can really be helpful if you're writing a larger simulation. You can look at the results and hopefully that'll point you in the direction of certain things are working, so those functions are probably okay. Other things aren't working, so that function's weird and I need to go look at it. So I'll just wait here for a moment for you to catch up with anything we've got. All right, I'm going to switch over to Excel for a little bit because we're going to look at a different way of writing these functions, which really comes down to just saving them in a different place, but it does have slight impacts on the way that we can use those functions. So I'm going to close the figure. The thing to note is that script A, which we've got over here in our current folder, that will not run unless those other 4 functions are present. So I need a total of, well, sorry, if those other 3 are not present. I need a total of 4. I need the script, the update position, the check right, and the check left. That's kind of a pain in the neck, A, because I have to go check all of those files if there's a mistake, and B, if I want to send it to somebody, I got to send all of the files, and they got to make sure they're all located in the right place. That can be really good if your simulation is big and multiple functions are calling on other functions. Then it's helpful to have something like that. In most of the kind of homework problems that you're going to solve over the next 4 years, that's not the case. Usually it's I have a well-defined problem and I might need 1 or 2 functions for it. So why not let the functions ride along with the script so that I don't have this mess of functions over here in my folder. If it's a bigger simulation, yeah, you'll probably do this because it's convenient. But the majority of the time, we don't need that level of flexibility. We can get away with a slightly more condensed or contained setup that allows it to sort of move around a little bit easier, or allows us to organize things more easily. That something, let me make sure that switch, is called a local function. So this is where we were looking at the end of class on Wednesday. We had talked about how standalone and local functions work. I'm going to duplicate this and modify it a little bit specifically for local functions, which won't take much, but I want to point out a couple of variations. So these are local functions. I'll change this to local. This is still true. Scripts still use the base workspace when you're dealing with local functions. There's still, the functions themselves will still have one workspace per function. This is a weird one. This will still be true. The data will still be passed back and forth between the workspaces as inputs and outputs, despite the fact that they're going to be written in the same place, which will look a little bit funky, and that's what we're going to draw here. So let's redraw this a little bit. We're only going to do it for one function, although, as we'll see in a moment, you can write as many local functions as you want, but it's easier to visualize if there's only one. So we'll get rid of all of this. Instead of this base workspace, we're going to call this the script. The variables created here are in the base workspace, which I guess I didn't have to type because it turns out I wrote that directly underneath there. So where do we write function A? Well, if we write function A as a separate file, that's called a standalone function. To write function A as a local function, you just write it at the bottom of the script. That's it. That's all there is to writing a local function versus a standalone function. The inputs and the outputs still work in a similar way. So outputs get sort of fed out of the function workspace, and inputs get put in from the base workspace. So that transfer of information is still the same. It's unchanged whether you do that. That's what I meant when this statement is a little bit weird. The local function is written inside of the script, but it can't see the variables inside the script. That's not a good thing or a bad thing. That's just the syntax of local functions. That's how they work. So they do not have access to the variables inside of the script. The only thing that you can do is the same thing as you can do with standalone functions, which is pass values back and forth as inputs and outputs. So that's where it'll go. It has to go at the bottom. So I'll leave that here. Local functions must be written at the bottom. I can't see my cursor on. I didn't realize how much I rely on my cursor until you can't see it while you're typing. A couple of updates down here. The general syntax doesn't change at all. That's still how we write a local function. It's just stored in the script. This is one requirement that goes away. So within the script, yeah, all of the functions have to be unique. But I can have a script with function A, and then have another script with another function A, call them exactly the same thing, and they can be completely different. The local function is only available to the script in which it's written. It can't be accessed by any other scripts. Because of that, you can rename the name. You can reuse names a lot, which, believe it or not, is pretty helpful because it gets hard to recreate names over and over and over again. This still holds. You can have as many inputs and outputs. You can have basically any structure. It's still a full function. You really don't have to worry about the current folders and working directories and all of that stuff, so I'm just going to delete that. As long as you don't reuse the name inside of the script, nothing else will ever see it, so otherwise you can rename local functions. Same rules here for inputs and outputs. That's okay. And again, I will just highlight the variables in the base workspace, even though they're written in the same script, are not available inside of the function. They're not there. The structure of the local function as I said a couple of times, is not much different from what we had with a standalone. It's just where they're saved. So let's come over here and give ourselves a new folder, and we'll say, what's this old one? I'll call this standalone. And we will throw everything that we just did into the standalone. So script A, update, check right, check left. We'll go in here. I'll delete those other two scripts if we want. So up here in our current folder, which is essentially empty, I'm going to create a new script, and we're going to call this one script B. This script uses local functions. Again, you don't have to make that declaration. It's not like MATLAB won't know it if you want to use a local function. It's just for our purposes of keeping track of things. The script itself is going to be identical to script A, at least on the top portion. So I'm just going to copy all of this code from part A, or from script A, and put it into script B. The only thing that we have to do now is bring the functions in too. So since we've already written them, we'll just copy paste them, but normally you would have to write them at this point. I find it exceptionally helpful to give this what kind of like a super comment inside of MATLAB. Remember, the local functions always go at the bottom. So I like to use a double percentage sign, and then that makes the comment bold. And it also draws that helpful little horizontal line and says everything that comes after here is a local function, which for me helps distinguish between what's sort of the actual calculation that's happening up in the script part versus all of the sort of helper stuff that comes down at the bottom. It's not that it's not important, it's just a nice visualization tool to separate the two. To put the functions in here, we can just copy paste. So we'll take the update positions first and copy that over. Don't forget the end. You always need the end in there. And then we'll take check left first. And I'm doing check left first to illustrate a point that I'll come back to here in a moment. The amount of white space in between there does not matter. I am in the habit of putting 2 white spaces, but that's just so that I can find my functions. And there we go. That is all of the functions that we need. So I can go ahead and close all of these other ones because I don't need them. This is sort of the local function syntax, and it's pretty standard, right? There's a bunch of script stuff up here at the top. All of this stuff is going to go into your base workspace. It can read from the base workspace, it can write to the base workspace, but everything that happens underneath that, where I've started local functions and then writing functions, those are all functions in the usual sense. They can only operate on what's given to them as input, and they can only return whatever you've defined as an output. They can't see that workspace, even though they're in the same file. So if you tried to access like n, right, if you wanted to read n down here in one of these functions, it will have no idea that it's there because it's in a different workspace. So if I run this, I'll get exactly the same thing, which is sort of a null result. It's a good thing that we got the same thing, but it's not actually doing anything any different. It's just an organizational tool. Again, it becomes primarily a question of whether or not you find it helpful to write the functions. The code will run at the same speed regardless of whether they're there or not. Yeah?
Did it operate the same because you're referencing those functions within the for loop up there and at the bottom, or do you not need those?
Oh, so actually, thank you for bringing that up because that was something that I said that I would address and then I failed to address it. Yes, it is running the same way. So the way that MATLAB looks for functions is it will run down through this script. It'll find zeros. That's its own function. It's built in. It'll always find those. Then it'll get down here to update position. It has its own method of checking. The first thing that it will always check before it even checks built-in functions is that thing a local function? So the very first thing it does when it sees a function is update position, it looks at the bottom of the script and says, is there something down there called update position? If it is, it temporarily jumps down there and does its little math inside of that function and then comes back up to the script. you don't have to tell it to jump back and forth, and you also don't have to organize it. So for example, here it's going to call update position, then right, then left. But the way that I put them down here was position, then left, then right. Right? It's opposite order. It doesn't care. They can come in any order. It will still find them correctly. Where it would go after that, if it couldn't find it as a local position, then local function, it'll then check your current folder. If it's not in your current folder, it'll check your whole path. And after that, it'll usually say, like, I am out of luck. I can't find whatever it is you're talking about.
And so this is beneficial if you have like a function created and you can't call it because it's not in that folder. You can just copy and paste that function within Husker.
Yes. So, for example, if you wanted to turn this in as homework, the only thing that you have to send me is script B. Right? There are no other files that have to go along. If I asked you to do something like this one, script A, there are no other functions in here, so you have to send all the other ones, or you'll get an error when you try to run this.
Okay, thank you.
Mm-hmm.
You have pretty long functions. Should it be better to use separate files or still?
So for anybody on Twitch, the question is it better to use standalone files than local functions? It's entirely up to you. The computer won't care one way or another. It's only the practical implications of how do I find the function, and then if I need to send it to somebody, for example, how easy is it to send it to somebody? It entirely depends on the application and really personal preference, because the computer doesn't care. It has zero impact on execution speed. You can do either one. It will be remarkably helpful when we get to these next few topics next week of solve the function for X. Those functions, we need to write functions for each one of those, but they don't really have any meaning, right? Here we wrote something and it's update position, right? There's a clear meaning of what we're doing in that function. These ones that are coming up, they're just like, that's the function I need to solve. Like it doesn't have any, I don't know, meaning in terms of a simulation. So it gets remarkably hard to come up with like dozens of meaningless file names and then keep them separate. So what you can do instead with a local function is you can just call them all the same thing, right? I'm in the habit of saying like my function for all of them. And that's okay because they're all stored in separate local functions, so they don't see each other. That's a surprisingly helpful thing to be able to do. So I have no need to introduce an entirely new math topic in the last 5 minutes on a Friday afternoon. So we're going to wrap it up here, but just as a heads up of where we're going, it's math. It's not math in the sense that you need to be able to do math. It's we're going to solve math-style equations, right? The classic solve for X style that comes up in all kinds of classes. We're going to focus on the first one is solving for one variable and then solving for multiple variables. And we'll look at variations on that as we go. So we're going to transition to more of a practical sense and further away from simulations like this. So if you like for loops, I'm sorry, we won't use them as much. If you hate for loops, good, we won't use them as much going forward. It won't be as necessary going forward. So have a great weekend for everybody on Twitch. I'm still over in Canvas chat. If you have any questions on anything, I'm happy to help out. But otherwise, I'll just hang around for a few minutes, and then I will see you back here on Monday. Good luck with your midterm, too. Bye, all.